All right. A pleasant afternoon to everyone, colleagues, friends, and students, and welcome to the IAG regional webinar for East and Southeast Asia in celebration of this year's International Geomorphology Week. My name is Noelina Ramos, and I'm from the National Institute of Geological Sciences at the University of the Philippines, and I will be co-chairing this regional webinar with Professor Takashi Oguchi from the University of Tokyo. Hello, Professor Takashi. Before we formally start the webinar, I'd like to call on our IAG President, Professor Sunil Kumarde, to say a few welcome remarks.
Thank you, Namla. Thank you, Takashi. On behalf of the International Association of Geomorphologists, I welcome all the speakers, participants, and the chair and co-chair of organizing this webinar in East and Southeast Asia. This International Geomorphology Week started since 2020 to memorize our legal status, which we got in 2019. And after that, every year in the first week of March, we celebrate this. It is not an easy task to organize this conference, but organize this webinar. This year, Takashi Oguchi has taken the lead to organize this International Geomorphology Week. We have divided the whole world into 10 zones. Along with that, we will have on 8th March, on the day of International Women's Day, we will hold another webinar, that's Women in Geomorphology from the Hellenic Committee of Geomorphology. I thank Takashi and as well as to Susan Conway to support technically to organize this International Geomorphology Week. So with these few words, I once again welcome you. And I think the session should be started with your comments. Thank you very much.
Thank you very much, Professor Sunil Kumarde, our IAG president. And now I call on my co-chair, Professor Oguchi, for a short introduction.
Yeah, thank you for attending this webinar for East and Southeast Asia. Yeah, I'm co-chairing this session with Noeliana. And yeah, as President Sunil Kumarde said, I have been responsible for organizing this series of webinars, regional webinars. And this is the third year. We started this in 2001, yeah, during the pandemic. Yeah, and the situation changed a lot since then. Now, yes, we can more easily meet in person. For instance, we had our, conference, IAG conference in Coimbra, Portugal, in September, in person. Yeah, so yeah, we have some discussion. Yeah, whether we should kind of keep on this kind of online webinars, but surely this gives lots of opportunity. Yeah, without paying money or travel cost, we can meet like this way. Yeah, for instance, currently I'm not in Japan. I'm in Romania. I'm actually collaborating with another IAG vice president, Mihai Miku, and but still I can join like this way. So, and we're really happy to see, already 50 people joined to this webinar. So, even today, yeah, I think this kind of activity has lots of demand. So, yeah, I think next year also we're gonna, organize something like this. And so, I really appreciate your participation, yeah, to this one. Yeah, and please, if you have questions to the presenters, we have wonderful, 6 presenters today. You can ask either by turning on your microphone or by chat. So yeah, we have about 2 hours scheduled. Yeah, but if we have a good discussion, yeah, maybe it's a bit of extension is possible. For instance, I attended South Asia and West Asia webinar, which President Sunil Kumar De was the main convener, and because of lots of discussion, I think it was also a little bit extended. So we come to that kind of situation, but also, for each presenter, I ask, keep your time. So, okay, so that's all from me. And so, Noelia, would you, yes, keep on.
Okay, thank you very much, Takashi Sensei, for giving us the quick introduction of the webinar, and thank you for spearheading this event. And again, thank you to our IAG President, Professor Sunil Kumar De. We are delighted that you are here to join us in this webinar. All right, so now we can proceed with our presentation. So as Takashi Sensei mentioned, we have a wide range of presentations this afternoon covering the various geomorphological environments and processes. So as you've probably seen in our program, so from mountains and hill slopes all the way to coastal environments. So with that, I'd like to welcome our first presenter, Dr. Noriko Hasebe, and she will be talking about thermochronology and will be briefly showing us a case study in Japan. Professor Hasebe.
Okay, the participants and chairmen, thank you for giving me this opportunity. Here you will find the copy of the leaflet of my institute. My name is Noriko Hasebe from the Institute of Nature and Environmental Technology, Kanagawa University. And you will find the research network in East Asia and Southeast Asia. It is my great honor to contribute to today's EAG session. Before starting, I would like to introduce myself first. Okay, I received degree from Kyoto University and worked in Kanagawa University nearly 30 years. So I'm very old girl. The photo here is the southern campus of Kanagawa University, and my office and laboratory locates somewhere here. During my career, I had a chance to work in University College London and also Korea Institute of Geology and Mineral Resources. My research interest is use of geo and thermochronology in various geological targets, including volcanoes, fault activities, accretional complexes. And I also work in paleo-environmental changes. Recently, I studied in Mongolian lakes together with my colleagues from Kanagawa University, Tokyo Tech University, Kochi University, Geological Survey of Japan, and National University of Mongolia. One of the speakers today is Dr. Davaadorj from National University of Mongolia, and we are collaborating for more than 10 years now. Because he speaks results of Mongolian research, today I would like to introduce how geochronology is useful in geomorphology, especially to estimate long-term erosion rate. Just for introducing myself, here I also show you some of equipment I'm using for geo and thermochronology analysis. I use the variety of microscopes, mass spectrometry for chemical analysis, and luminescence reader for TL and OSL analysis, dating. And they are photo of fission tracks and luminescence found in minerals and useful for dating. Okay, now I would like to remind you how we can estimate the age of samples or event. We use the radioactive decay. This figure shows how amount of radioactive atoms decrease through time. When the half-life passed, the amount of atoms becomes half of the original. And additional half-time passed, it becomes decreases to 1/4 of the original. Instead, the daughter products increase. By analyzing both, we estimate how many half-lives have passed. In other words, age. But now we must consider what makes the start of the system. We say clock switch is controlled by temperature. When temperature is high, elements or atoms which constitute minerals or rocks moving in and out. And we can't apply radiometric dating for samples of this situation. When temperature is low, elements are trapped in the mineral or rock, and the change in the number of atoms only controlled by the radiometric decay. We call this situation as a closed system, and the temperature as a closure temperature or locking temperature. Therefore, the start of the system means when temperature becomes lower than the closure temperature. This is the list of dating methods and the closure temperature here. Zircon uranium lead dating closure temperature is as high as 800 degrees C. And low temperature methodologies have closure temperatures like 100 or even less, and they are useful for geomorphology. This closure temperature is determined by the laboratory experiments. Samples are heated and analyzed repeatedly to see the behaviors of dating system against the temperature change. And using this Arrhenius relationship with vertical heating duration and horizontal heating temperature, temperature conditions necessary to make the system closed in geological or geomorphological timescale is estimated. The other way to estimate closure temperature is analysis of natural samples with known cooling history. In this graph, one sample was analyzed with variety of methods. Vertical is closure temperature of each method, and horizontal is obtained ages. Cooling history is derived by analysis of method with known closure temperatures. Then age by the method without information of closure temperature is plotted on this figure, and we can estimate the closure temperature. Now, we all know the Earth's interior is hotter than the surface. Imagine this is the cross-section of subsurface underneath the Earth. With geological thermal gradient of around 20 to 30 degrees C per kilometer, temperature increase. And temperature here is comparable to the closure temperatures of the dating system. let's imagine a sample was here. Also imagine the closure temperature of the dating system is here. It's only for a particular methodology. When the surface part here was eroded away, the sample position relative to the surface is moved up. And the sample cooled through this closure temperature, and the clock starts to tick at that time. When amount of erosion is small, this sample is still below the closure temperature. Now we collect samples from the surface. The age obtained, age we calculated by the analysis is represents how many years were necessary from this closure depth to the surface. The sample moved up to the surface, and how many years necessary to move up from here to here. Fast erosion area show young ages, and slow erosion area should show old ages. This is why we can estimate the amount of erosion from the geochronological methodologies. Okay, in tectonically active zone like Japan, we have high mountain ranges due to compression between Pacific plate and Asian continents. Erosion process is also very intense, and amount of erosion is subject to tectonics and also climate, rain, river, landslides, etc. In case of mountain building and erosion, mountain slope also should experience the cooling through the exhumation processes. Now, I would like to show you some research examples. The first is a result from one locality analyzed by several methodologies. The second one is analysis using one chronological method, but analyzing many samples together. It's also possible to extract some information on the erosional processes. In fact, this is the same plot I already showed you as an example to estimate the closure temperature of a particular chronological method. This is the example from European Alps by Harford, 1986. Cooling rate, this part is around 100 degrees C per million years. Assuming geothermal gradient of about 25 degrees C per kilometer, the erosion rate is about 4 millimeters per year. And the recent erosion, because of the slope is shallow, the erosion process was slow for this example. So this is how we estimate the erosion process from the chronology. This is second example, many sites with one methodology. This chronological mapping is compiled by Sueoka and Tagami. In this map, two methodologies with closure temperatures of 100 degrees C and 250 degrees C is plotted. Young ages are indicated by a reddish color, and old ages blue colors. And I also, my data is also included this compiled map. And if I only extract the my data with the method closure temperature of around 100 degrees C, and this is the Japanese islands, and if I analyze the data samples from this area, the ages were around 10 million years old. On the other hand, in this area, they are very young and less than 1 million years old. We can calculate the erosion rate in this yellow region, assuming some geothermal gradient, and it's about 0.4 millimeter per year. While in this wet area, because the age is much younger, meaning the erosion rate is much faster, maybe 10 times faster than this area. And this difference is interpreted as a result of collision of this volcanic arc to this Japanese island. And this is the average sedimentation rate in the artificial reservoir. And it's categorized in each district in Japan. And I'm sorry, this is in Japanese. And Hasegawa-san from the National Research Institute for Earth Science and Disaster Resilience summarized this data. And this yellow circle is corresponding to the area colored yellow in the previous slides. And the order of erosion rate is similar with the data obtained by Geomorphology. This red area contains the area where erosion rate is high. Sedimentation is high compared to yellow area, although it's not that much high, not 10 times more. When I look into the data summarized in this paper, the nearest reservoir to my research area has the higher sedimentation rate of 3.45. So I think the chronological method and this method can show some comparable results, consistent results. Next, shortly, I would like to introduce an example of data collected along the vertical profiles. Research was done in this mountain range. In fact, my university located here is very close. But in this figure, ages are plotted against the elevation. And this is PhD study by Yamada-san. He's my junior colleague when we are both PhD students. I only helped sampling by climbing mountains. And in this area, erosion rate was very fast, becomes very fast recently. And the interpretation is it's probably related to the active tectonics. Okay, so now I think it's almost more than 15 minutes and I must summarize my conclusive comments. I only give very simplified talk and ignore the detailed description. In fact, we must consider the geothermal gradient changes through erosion. And we also consider igneous activity. And some of geological methodologies provide additional information, not only ages, but more detailed thermal histories, but I didn't mention anything about it. Anyway, I'd like to insist that I hope some enhancement of collaboration with geomorphologists and geochronologists. And this collaboration will bring us further knowledge on the geomorphological evolution of particular research area. Okay, thank you very much for your attention. Sorry, I'm a bit long to talk.
Thank you, Dr. Noralina. Hi, everyone. Myself, Dr. Yunus. I'm presently working at the Indian Institute of Science, Education and Research, Mohali. Indeed, it's my honor to be part of this International Geomorphology Week 2023. I'm thanking Professor Takashi Oguchi for inviting me here. So today I'll be presenting my work that I did during my stay in China. So I worked on this Wenchuan Earthquake affected region in part of the Sichuan Peninsula, Sichuan region. So yeah, just a brief introduction about me. So I'm presently working with ISER Mohali and heading this Geomorphology and Mountains Lab. And I'm interested on earthquake-induced landslide, rainfall-induced landslide, and sediment erosion problem. And I obtained my PhD from Professor Takashi Okuchi's lab, Center for Spatial Information Science, in 2014. So this work which I'm presenting today is more about the earthquake-induced landslide, in particular the post-seismic landslide. So everyone might have heard about this disaster, one of the biggest in terms of the number of the landslide triggered during an earthquake. So this is Wenchuan Earthquake that happened in 2008. This earthquake triggered more than, there are different mapping inventories. One of the inventories shows that there are 100,000 landslide was triggered during the Wenchuan earthquake along the long mentioned mountain chain. And this, after this earthquake has happened, a lot of studies has carried in this region. And a summary of the study shows that the earthquake not only triggers, simultaneously triggers the landslide, such as rockfall, landslide, debris flows, etc. But over the time, so once the seismic phase is over, days and months after the main earthquake event, you can see that there is a post-seismic debris flows, landslide damming. Then this landslide dam breaks, which leads to a dam break flood. And over the time, decades and years and decades later, you can see that the flooding has been increased in the downstream regions. Then there is a rising in the stream bed, which causes by the sediment that is deposited from the earthquake as well as the post-seismic situations. And these post-seismic landslides are mainly triggered by rainfall because a large amount of the post-seismic material is available in the hill slope. And during the rainfall event, heavy rainfall event, they are mobilized downwards, causing a post-seismic debris flows. And these debris flows are highly hazardous because people are unexpected about these deposits, and they wash away the villages and their infrastructure down. So these post-seismic event, once it happens, the post-seismic condition that stays for days, sometimes months, or sometimes even decades, and it continues up to centuries until a new earthquake happens. So this is the summary of a study by Fanital, that is after the Wenchuan earthquake is take place. And by post-seismic landslide, what I mean here is that during the post-seismic landslide that is triggered by the main earthquake event, you have a large amount of deposits that is taken out from this hill slope, from the mountain. And where this material, for example, this is the Jain Dagambo landslide. It's a volume of approximately 1.35 billion meter cube. And the height is about 600 meters for this particular case. And where these materials are going down, these materials are after the seismic landslide is triggered. These materials are now, you can find in the hill slope. They're deposited as a debris in the hill slope. So as I mentioned, there are 100,000 landslides are triggered in this particular region, in the Wenchuan region in China. And there are about, you can see that these all materials are now deposited in the hill slope. And these materials, the properties of the material is that they are loose. They have fine sediment as well as large coarse boulders. So the process is that during the initial rainfall condition, even though the rainfall is, amount of rainfall may be lower, these fine materials will be immediately transported down and causing a debris flow. And over the time, these fine materials will be transported, but remaining is the coarse material. And for moving the coarse debris, you need to have a higher amount of rainfall. So the higher amount of the rainfall, whenever it happens, these large boulders will move down. Now, this is the case, the debris remobilization. It happens after the 2008 earthquake. There are two major rainstorms. One is in 2010 and another is in 2013. So both these rainstorm has triggered more than about 6,000 or more debris flows in the region. And you can see some of the glimpses of these debris flows. They are since the water is involved, the materials move down very fastly, and they have washed down the entire villages downstream. So this become a major problem here. So I show some of the photographs of seismic phase here. This is the after the 2008 Wenchuan earthquake. You can see these are the landslides that is triggered by the earthquake, and some military activity, that the rescue and relief operation is going on. And you can see that in 2010, after the major rainstorm, this area, the most of these seismic deposits that are deposited in the hill slope, they have washed away the entire region. So this is a photograph taken after the 2008. And this is another photograph, which you can see that a large number of landslide in the hill slopes here, and these materials, when they are in the hill slope and in the channels, they are easily mobilized during the subsequent year rainfall season. You can see that many people didn't expect this to come down, and they, after the earthquake also, some people tried to live there, but they were washed during this post-seismic debris flows. This is another example. An entire village is washed away by this Wenchuan gully debris flow. Another example where you can see that the riverbed is risen by the materials that is caused by these debris flows, and that has now increased the flooding chances in this region. So this is what the situation is after the Wenchuan earthquake. The post-seismic landslide are causing a large trouble there. Another example from Ting debris flow in 2010. Again, you can see that all along this valley, the villages or these towns are now washed away. So there is an important need to study this post-seismic landslide and debris flows. And if we see these global cases of landslides, earthquakes, there are only handful of studies, less than 15 cases, has so far studied the post-seismic landslides. Primarily, this is the lack of these studies because of the availability of data for the post-seismic condition. And two major cases that are studied for the post-seismic are, one is the 1999 Chi-Wen earthquake. A large number of studies has carried on the post-seismic condition, because there are a lot of triggers of the from the typhoon events. They triggered a lot of debris flows there. And after that, it happened for the 2008 Wenchuan case. So our aim of the study was to predict this post-seismic landslide, because it is a big problem in the region, and we try to predict the post-seismic landslide. We aim to try to predict the post-seismic landslide in the region. So that's what this talk is about. To predict this post-seismic landslide, we collected an inventory of these post-seismic landslide from 2008 to 2018. So we systematically map all the landslides, post-seismic landslide, pre-seismic landslide, as well as the post-seismic landslide. And we categorically mapped them as 4 classes. So A0 in the sense, if there is a post-seismic landslide and if they have not remobilized or they are stable after the main event, we can call it as A0. And A1 is that if the post-seismic landslide material is, if it is about 25% is mobilized, we call it as A1. A2 is that 50% of the material is mobilized, and A3 is more than 50% that is mobilized in the region. So accordingly, systematically they are mapped. This is another example showing this mapping. So in the remote sensing, we use the high resolution satellite imageries to map the post-seismic landslides. And in the imageries, you can see the bright spots. We consider it as the, for example, in this case, this is the post-seismic deposit, and this is the remobilization. So I'll just put the pointer. Yeah, so this is the post-seismic deposits, and this is the remobilization. And this remobilization, you can see has a bright spot in the satellite images. So we map all the pre-seismic landslide, that is the landslide that is happened before the earthquake. So 2005 and 2007 is these maps. And the right one is the post-seismic, that is the 2008 earthquake. So you can see that there are thousands of landslide in this particular catchment area. And in case of pre-seismic landslide, they are mainly triggered by rainfall. They are less in number. And this is the systematic mapping of the post-seismic landslide, where you can see that these red zones are the areas where 50% of the remobilized materials are there. White ones are the dormant, where the post-seismic materials are stabilized. So these are mapped for 2011, 13, 15, and 2018. And this is the number of these landslide. You can see that in 2005, there are 156 landslide. Sorry, this is area. Here is the number. There are in 2005, there are 133 landslides. In 2007, 71. But in 2008, you can see that the number of landslide, the post-seismic landslide is more than 8,000. On the subsequent years, we map the channel deposits, we map the slides and debris flows. This is the number of these debris flows over the time. Year 3 is the highest level. So in the initial year, it was highest, and following years, it gone down to the pre-seismic condition. And this is the size frequency map for the landslide areas, frequency density. And this is the distribution map, landslide density map, which shows 2005, the deposits are, landslides are sparsely distributed. In 2008, this is the condition. The red areas are the high density landslide zones. And over the time, these landslides concentration has decreased, but not to the pre-earthquake level. And you can also see that when we map this landslide, we also see that because there is even with the smaller amount of rainfall, the rainfall threshold, there is debris flows. So that is now going back to the pre-seismic condition, but not yet to the level in 2018. And every time when there is a large rainfall, rainstorms, we expected many debris flows in the region. And we apply a machine learning model to predict the post-seismic landslide. And we tried different models, and we find that random forest, that's one of the best model for the prediction. And we applied that to our study area, and we used following factors: elevation, slope. So these are the general factors, general topographic factors. We also use the seismic factors like PGA, PGV, peak-ground acceleration, velocity. We also use, in the post-seismic cases, we also use factors like the volume of the post-seismic deposit and the area of the post-seismic deposits. Then the rainfall as another factor. So what we find is that when I use the 2008 data to predict the 2011 debris flows, I could able to predict it very nicely. The accuracy is good. But when I try to predict the 2008 using 2008 data to predict the 2013, there is a decrease in the predicting capability, and after like for 2015 and 18, further it is decreasing. Again, if I use 2011 to predict 2013, it's give me a good result. But when it goes to the later stages, the prediction capability changes. So we need to know why this prediction capability is decreasing, and we tried another machine learning function that is variable importance or information gain function. And what we find is that over the years, the prediction factor importance changing with the time. So in 2005, 2007, you can see that rainfall was the most important factor. And in 2008, it became the post-seismic landslide. And in 2011, 13, 15, etc., you can see that volume of the post-seismic landslide was the most important. And over the time in 2018, the distance to stream become the, so now most of the deposit are, post-seismic deposit are moved to the stream, and that becomes the important factor, and the elevation and slope are the important factor in 2005 and 7, but it reduced, and over the time now it goes back to the 2018 situation. So this is what our finding is, and this was validated with the 2019 event. Almost all the debris flows that happened in this region is now in the channels. That's validated our findings that now most of the deposits are in the streams. And that's all about my presentation. Thank you for your attention. I acknowledge my postdoc supervisor, Professor Chi-Wen Chen, and Shukyan from SKLGP, and Professor Filippo from University of Padova, and students of CGP for helping in this work. Thank you, everyone.
My name is Davaadorj Davaasuren. I am the lecturer of the National University of Mongolia, Department of Geography. Yeah, my research background is the geomorphology, geography, and soil science. Since the 2014, I cooperating with the Hasebe-san from Kanazawa University. Then I very interested about the water quality, long-term monitoring, file environment, reconstruction, and other so many interesting things. Then today, I want to introducing some of work with the Hasebe-san and Kanazawa universities. Then we just using the some remote sensing data to extract in the lake water surface areas and to trying to detecting the water surface using the lake depths, volume, and area changes. Yeah, our cooperation work is started with 2014. It's working on the some saline lakes in Southern Mongolia. Then these lakes are so very big resource of the drinking water and other water, surface water resource in Southern Mongolia. Also, these lakes are very sensitive with the like regional climate change or some other with meteorological impact. Then we trying to using the continuously long-term monitoring to detecting the lake surface, just lake water surface area, trying to change it. Example, this one is that some researchers mentioned that the saline lakes in the Southern Mongolia, especially located in the red areas lakes, are strongly decreasing the areas. They mentioned some of lakes are shrinking the summer years, and they said it's very quickly decreasing the loss in the water surface area. Therefore, we will try to the understanding this continuous measure. You try to measure the continuous monitoring. The one of interesting is that this research from the Hasebe-san's laboratory, researcher Yunus, she mentioned that in the arid areas, open environment lakes are very sensitive to this water quality changes. Because the southern area of Mongolia is indicating the semi-desert weather. It's high amount of runoff, washing, wind transportation, some kind of organic materials, and increasing the water salinity from the evaporations. It means this meteorological condition and meteorological events directly impacting the water quality or water areas. Like this kind of purpose, we selecting the 3 different lakes in the Southern Mongolia. Most of the big lakes in the between the some open wide valley in the 2 highest mountains area, in Bonsan and Org Lake. It's most of the very highest lakes, biggest lakes in the Mongolia, and the area is the total area is the covering more than 100 kilometers. Wenchuan is the 240 kilometers square. And the other thing is the some permafrost lake in the mountain area. It's very smallest lake, but it's 1.3 meters square areas. Then one thing is that we will try to understanding ecological impact on this arid environment. The second one is the trying to understanding how to remote sensing detection can be working in the big, small, mid-sized lakes. 100 kilometer, 200 kilometer on 1.5 kilometers lakes. It's so interesting topics. Also, these three lakes is one of our study area for the joint researchers. Just last week, we just go in these lakes again to checking the water quality. It means this water monitoring is since the 2014. Until now, it's continuously measuring the water and ice, lakes, so many topics still. The lakes are looks like this. The Alga is the smallest lake, 1.5 kilometers. Wenchuan is the biggest one, 240 kilometers square. Orb is the 100 kilometers, but it's very changeable one. It's very shrinking lake. Sometimes it's very easily disappear. Yeah, and our study is based on the remote sensing. Then we will trying to continuously measuring. Then we will using the Landsat Edlic data since the 1978. Then we will using these different band maps for the using the detecting the water for the lake areas. Stuff like this. We're using the vegetation indexes for the getting the water information and water index and enhanced water index in the three different areas, but trying to detecting water changes in the satellite images. Yeah, we're just using the different kind of maps, using some kind of indexes, and trying to do some detecting classification techniques, extracting the lakes. We also try to comparing some kind of different maps, topographic maps, type of rulers like this. Recently, there are so many researchers have been developed to using the water surface areas data for trying to the depth changes, lake volume changes. Also, it can be using the water balance or some kind of influences. And we also trying to using these methods in our research. Yeah, because this is some kind of our this is some of our results. Because recently, last 2 or 3 years, sometimes inflowing lakes are disappeared. The lake areas really strongly, quickly changed in the area. Yeah. First, we're using some water index from the 3 different lakes and vegetation index. We are trying to 3 different indexes to detect this continuously measuring. Our measuring time is usually in August, because August is the more raining, wet season in Mongolia. The most of lakes receiving the high amount of water. It's more highest water supporting season in Mongolia. And this is our first draft data. We're just trying to each year's available maps to detecting the lakes. Then 3 different methods to detecting. Then trying to get informations. For example, in Wenchuan Lake, 3 different index have been showing the similar changes. There are some kind of 4 different period on the results. An example, 1980 to 1990, the lake area is more stable. They are changing so very slowly. But after the middle of the 1990, some years are receiving so much water to increasing the water areas. After the 2000 to the 2017, it's quickly decreased. It looks like 290 kilometers square areas decreased 40% until 240, 270, like this kind of decreasing. And after the 2017, it little bit, I have to say, not stable, but little bit changeable. But it's the some of biggest lakes. Second one is Davaadorj Lake. It's very near to some higher mountains, but area is around 100. But we have been detecting several shrinking in the lakes. 1987, 2005, 2010, 2015. The lakes are gone. And more highest region is similar with the Wenchuan Lake, because the water surface area has reached 140 kilometers square in around 2000. But after this, it's only 8 or 10 years. It's the first 3 years. The other one is Davaadorj Lake. It's very smallest lake in the mountain area. This lake is some kind of very smallest. And we can't detecting any changeable in here. Only vegetation index will be changeable. It's some kind of green color, I guess. Then we will try to detecting the depth changes. If Wenchuan Lake increasing the areas, 2018. How about the depths like this? If the shrinking, decreasing the water areas, how many changes have been detected? Then our first detection is some kind of we have been detecting 1 meter depth changing in this lake areas, I guess. But I think we need more clear data on the field. If like this, if points are like this, Davaadorj Lake, if 140, the average depth is around 2 meters. Yeah, one thing is the example, this kind of lake depths, the zero is the just middle depths of the books. For example, Wenchuan Lake is 16 meters, and we will try into the meter or centimeters of changing the lake depths. Davaadorj, yeah, and with the shrinking, it's around 1 meter of shrinking the lake disappear like this. Yeah, our second thing is we based on this lake changes, which factor is the most important one? Yeah, we will trying to get different units detecting. Okay, this is some kind of statistical analysis. Some basic years lake areas. And first period, 2000, around the 2000, most of areas decreased. 2000, it's 17, it's been lost. After the 2017, it increased like this. And the other thing is okay. Then our next analyzing is which area is more sensitive to changing in the lakes. And based on the remote sensing analyzing, western area is the more changeable with the water surface areas. Okay, this is some kind of evaporation in the Wenchuan Lake or lake. most of waters came from the precipitation, and inflowing is a little bit, how to say, it's changeable. Somewhere inflowing is very important, other years maybe precipitation maybe higher, I guess. Yeah, I think that's just some kind of our results. Our next work is to try and understanding how to developing the remote sensing areas connecting to some water quality change, so other things, I guess. Okay. Anyway, thank you guys. Thank you very much. I think it's all for today.
Okay, thanks for the introduction from Professor Oguchi. I'm Chi-Wen Chen from the Department of Geosciences, National Taiwan University. And I'm very glad to give a talk here today. And I would like to take a case 2022 Taitung earthquakes in Taiwan to share our finding about the distribution of earthquake-induced landslides, especially in relation to active faults and topography condition. Okay. About the 2022 Taitung earthquakes, we described these earthquakes as a series of two earthquakes affecting Taitung and Hualien County in eastern Taiwan. And the largest force shock occurred at 9:41 p.m. on September 17th. And then after about 17 hours later, at 2:44 p.m. on September 18th, the main shock occurred. And many aftershocks, or we can say foreshocks, occurred between these two earthquakes. Okay, this is the distribution of the PGA of the two earthquakes, just for your reference. And about the earthquake source fault, okay, the island of Taiwan is the product of the ongoing collision of Eurasian plate and the Philippine Sea plate collide in this way. So the fault system in eastern Taiwan is affected by this oblique collision, and the fault system of eastern Taiwan, there are many two active faults. One is the longitudinal valley fault on the coastal range side, the east side. And another one is the central range fault on the west side, actually the eastern margin of the central range. So many seismic activities often occur between these two fault systems. So from the seismological analysis, some phenomena are found in this time. First one is the foreshocks and aftershocks are distributed along north-northeast, south-southwest direction. Okay, this direction, and the largest foreshock and main shock have a stress-relief faulting mechanism with a few reverse components, and also the fault plane are found that it's inclined to the west. there is sufficient evidence to confirm that this earthquake, the earthquake source fault is the central range fault. Yeah. And in fact, the earthquakes did not cause many casualties, but it did hit some buildings and facilities. For example, buildings were knocked down. Like this building, the first floor of this building is convenience or 7-Eleven. So you can see a lot of 7-Eleven escaping. And also, platform canopies of a train station collapse, and also this location of a bridge deck. And the key point to share today, landslides. Okay, this landslides was observed near the epicenter of the main shock. One of my colleagues, his research team was in the field working for other project and just took this picture. Okay, so after the earthquakes, the Soil and Water Conservation Bureau of Taiwan identified landslides using satellite images before and after the earthquakes. And a total of 45, not so many, but 45 landslides were identified. So the objectives of this case study are to analyze the spatial distribution of landslides induced by these earthquakes in relation to the central range fault, and also to analyze the landslide distribution on topographic conditions and to discuss the impact of topographic effects. Okay, the methods are quite simple. Now we have the distributions of the central range fault and landslides. So first, we measure the shortest distance between each landslide and the central range fault, and also distinguish its location on the hanging wall or foot wall side, so to clarify the relationship between landslide distribution and active faults. And second, in order to recognize a topographic condition of the landslides, so we use the 5 meter DEM for morphometric analysis of the landslide, such as elevation, slope, and aspect. Okay, the result of landslide distribution and the distance to active faults show that the distance between landslide and active faults ranges from about 0.8 to 17.6 kilometer, with an average of about 8.3 kilometer. And there are about 71% landslides distributed on the foot wall side, and about 29% of landslides distributed on hanging wall sides. Okay, so Chen et al. In 2022 proposed a model for assessing landslide distribution. And this model showed that landslide triggered by earthquakes show normal distribution with the mean distance and standard deviation from the active fault. Okay, that varies depending on the parameter of the active fault. And I will not explain in detail of this equation here, but you can see this is the equation for the normal distribution, and its mean distance and standard deviation are related to some parameter of active fault, like the inclination of the active fault and the fault top depths, and also the earthquake energy. And the earthquake energy is from the magnitude. Okay, this equation used the Japan Meteorological Agency magnitude. Okay, and from our statistics, the mean distance to the active fault is minus 3.5 kilometer, and the standard deviation is about 8.7 kilometer. And for the fault top depths, because we cannot we don't know this parameter, so we assume it is 0. And from this, then we can get we can calculate the inclination of the active fault is about 80 degrees, and the magnitude is about 7.3. So this result is consistent with the investigation of the central range fault and also the real magnitude reported. Okay, about the landslide distribution on topographic conditions, landslides mainly occurred on elevation between 250 and 750 meter, and also on slope between 45 and 60 degree, and slope aspect of east, southeast, and south. So from these results, we can find that landslides are located on relatively low elevation and steep slopes. So another important issue is about the distance from ridge and stream. Yeah, many previous studies pointed out that post-seismic landslides tend to cluster near a ridge crest. And this is owing to the fact that ground accelerations are amplified in both the topographic ridge and convex up necklines within ridge flanks. So it results in the highest landslide susceptibility near ridge crest. So we calculated the normalized distance to ridge by this equation. Okay, and the value vary from 0. It means the landslide located near to the ridge, and 1 for the landslide located closer to the stream. Okay, so however, we found that most of the landslide occurred on mid-hillside or even closer to the stream. So this result is different from the phenomenon that most post-seismic landslides occur near ridge crest observed by previous study. And so the central range fault has a high angle of inclination, and this kind of fault type landslide distribution will be mainly within 5 kilometers from the fault. However, the central range fault is distributed in the longitudinal valley, and the 3 kilometers from both sides of the fault is almost a flat area. So only 6 landslides distributed within 3 kilometers from the fault. So we think that seismic waves transmitted to distant mountains are weakened by the attenuation effect and are therefore not strong enough to have a significant amplification effect on ridge crest. Okay, so about the topographic effects, we found that most landslides are distributed at low elevation, which means the seismic wave can not reach farther high mountains to induce landslides. In addition, most landslides occurred on steep slopes, which also shows that when seismic waves travel farther away, landslide can only be induced on low stability steep slopes, owing to the weakening of seismic waves. And because of the comprehensive condition of fault mechanism and surrounding topography, landslide most occurred on the middle hillside rather than on the ridge crest. Okay, I think the time is almost up, so I will finish here. Here are 2 concluding remarks and for your reference. And thank you very much for your attention.
Okay, yeah, thank you, Dr. Chen, for very interesting presentation. So now it's time for discussion and the comments. Anybody? Yeah, you can write in the chat box or you can, yeah, just speak. Okay, so yeah, I have one question related to your discussion about the distance from ridge. So yeah, it's quite interesting, and you made a interpretation. Yeah, so that's why I think sounds reasonable. But do you think in this case the effect of underground water is totally negligible, even it's earthquake induced? If the water level is higher, maybe more susceptible to landslides, and in this case, if the slope is closer to the streams, yeah, so maybe the optimal distance is somewhere in between the streams and ridges.
Yes, yes, you are right. The groundwater level may affect the location of landslides, but actually, we didn't check the rainfall before these earthquakes yet, so I cannot tell you about the rainfall condition now, but I remember that not sure, but I remember that before the earthquakes, I think not so many rainfall. Before the earthquakes, so maybe the groundwater level have not so much effect. I don't know, but I need to check this. Yeah, of course.
Yeah, okay, thank you. Yeah, I think your explanation is acceptable, but there are maybe some other possibilities. So yeah, you can also take some more. Yeah, now we got one question from the Dr. Ace Matthew Katib. Yes, so Dr. Chen, can you read that one and can answer? Yeah.
If you found,
I would like to ask if you found a correlation between the landslide occurrence and underlying lithology.
Oh, yes. The research is also one of the factors may affect. Yeah, of course. yeah, this is important to check also, and I didn't check yet. But yeah, of course, I can use some maybe geological map or something like that, and to overlay with my the landslides, and maybe for more analysis. Yeah, it's good question. But I don't know. I'll say yeah, because most of the landslides occur on the mid hill, not on the ridge crest. So if some occurred on ridge crest and some occurred on mid hill, then I can compare. Maybe the lithology is different or something like that. But yeah, yeah, I need to discuss more.
And we got 2 more questions. Maybe Dr. Yunus Ali.
everyone. Hey, microwave please, something वाला.
Oh, Dr. Yunus, are you speaking?
हमने install कर दिया, work कर दिया.
He's speaking something different, right? But he did actually question.
Yeah, the relationship between PGV and landslides.
Yeah.
No, I didn't compare this in this moment. Yeah.
Okay, and there's one more from Laura and Joseph.
Say frequency and
vegetation.
Oh, vegetation. Okay. Vegetation cover is also one of the factors, right? Yeah. Yeah, in this moment I didn't compare. Yeah, sorry about this.
Yeah, very interesting questions, because there are many factors affecting landslides. So
yeah. I just want to focus on the relationship between active fault and landslides. Yeah, and also some topographic conditions at this moment. But yeah, of course, I will check all of the factors you give the comment for me. Yeah.
Okay, so yeah, thank you, Professor Takashi, for the introduction. And good afternoon to all. It's Ting Zhang from National University of Singapore, Department of Geography. And it's very honored to have the chance to give a talk here. And my sharing today is about warming-driven erosion and sediment transport in the vertical regions. And this is about our research review work by me and also by my colleagues listed here. Okay. Well, as we know that the erosion and sediment transport from the cross-feed rivers are very essential for shaping the landscapes, maintaining the ecological health, regulating the biogeochemical cycling, and more importantly, they are impacting the security of the infrastructures and also the water, food, and energy supply for the vulnerable local communities, and also for billions of people downstream. However, now the ongoing cross-feed degradation together with increased hazards and disasters like everything have driven the significant changes in the sediment transport, and this will have far-reaching implications. And now the climate warming has led to the rapid glacier melting at global scale, and the glacier mass loss rate has also accelerated since the 1990s. And this accelerated glacier recession is also accompanied by over 50% increase in the number of glacial lakes and 30% increase in their extent. And this will further increase the risk of glacial lake outburst floods, and these outburst floods can further trigger the dramatic changes in the river channels and also mobilize a large amount of sediment in the short period. And the climate warming and earlier snowmelt also increase the permafrost temperatures and active layer thickness, like here and here at a global scale. And the rapid permafrost warming has been observed in the Arctic continuous permafrost and mountain permafrost. And the ground ice melting within this permafrost also expanded the extent of the erodible thermochast landscapes. And from the satellite images in 2007-2008, it's estimated that over 10% of the northwestern Canadian Arctic has been covered by the thermochast landscapes. And this overall crossover degradation is releasing large amounts of unconsolidated sediment from the frozen ground and also the glaciarized regions. And so here we illustrated their effects on the sediment transport processes. And in the glaciarized regions, the sediment can be mobilized by bedrock erosion, like here, and meltwater erosion and freeze-thaw actions. And with the climate warming, the increased meltwater input can facilitate the basal sliding and enhance the bedrock erosion. And the retreat of glaciers can also create more depository slopes with more frequent freeze-thaw actions in higher elevations. And they also expose the subglacial sediment storage. And however, the mobilized of this sediment, the mobilization of these sediments and can be disturbed by the glacial lakes, debris fan, and also vegetation recovery. And this will all lead to the disconnection and mutes the signal from these regions. And in the degraded permafrost, the sediments are mainly mobilized by melting of ground ice with the formation of salt slumps, active layer detachment, thermal erosion gully, and thermal back erosion. And efficiency of this sediment export from the disturbed thermochast areas is also largely controlled by the hydrogeomorphic connectivity. And this channel connected thermochast landscapes can disproportionately increase the fluvial flux until the landscapes are stabilized. So in our review, we compiled a global inventory to collect signals of enhanced erosion and sediment transport driven by the crossover degradation in the worldwide coast regions. And our inventory includes the 76 locations from the high Arctic, European mountains, and also high mountain Asia and Andes. And we also include 18 Arctic permafrost coastlines with accelerated coastal growth. And in this inventory, we confirmed the widespread increase in sediment transport from these coast regions during the deglaciation. And such increased sediment flux have caused multifaceted environmental and societal impacts. Like here, they can degrade, jeopardize the downstream hydropower exploitation by reservoir sedimentation and mechanical operation, and the retreated permafrost coastlines also leads to the irreversible land loss and land degradation, and muddy rivers also degrade the water quality, and associated increase in contaminants, nutrients, and organic materials will impact the ecological health and impact the carbon dynamics of the receiving waters. And once the sediment-laden flow enter into the flattened mountain mouths, the increased deposition will rise the channel bed and trigger the river eruption and more floodings. Well, then let's get into the signal from the different regions. Like in Himalaya, the warming intensified glacial recession are largely responsible for the increased sediment flux, and they're more sensitive to temperature changes in watershed with a higher glacial coverage. However, such impacts of glacial recession are not fully visible in the basins with poor connectivity like the front layers here. And in the outlier basins, the glaciarized sediment sources are distributed in the remote region from the basin outlet and are more distributed in the fully connected regions. And the similar phenomenon can also be observed in the European Alps. Like here, the nearly doubled cross sediment yield with glacial recession have shown in the right dots here. And while the observed volumes of the cross sediment export are much less than the estimated sediment transport capacity by the blue dots here. And this is because the rapid glacier mass loss region shown in the red color here, are mostly distributed in the poorly connected blue region here. And in the permafrost region, the retrospective salt slumps are recognized as the most effective thermochronology disturbance in increasing the sediment transport. And the widespread salt slumps and the signal of the increased sediment fluxes have been reported in many catchments from the Tibetan Plateau and also from high Canadian Arctic. Like here, we observed many channel-connected salt slumps in Toto River, and such extensive erodible landscapes, together with the increased rainfall and slope flushing, have doubled the sediment yield and sediment peaks over the past 3 decades. And in the Peel River, the number of retrospective salt slumps have also increased from nearly 200 in 2005 to over 300 in 2017. And these sharp increase in salt slumps have increased the contamination of the particulate organic carbon and also the sediment yield by up to 3 degrees of magnitude compared to the undisturbed regions. And in the polar region, the signal of the intensified permafrost erosion can be captured by the accelerated retreat of the coastlines. And the erosion rate is more than doubled in these 3 regions. And from the signal from this segment of the permafrost coast along the Beaufort Sea in the Alaskan Arctic, we can see a nearly 20-meter retreat of coastline just in 1 year from 2007 to 2008. And such intense coastal erosion and coastal collapse have enhanced the land-to-ocean biochemical flux, and also the nutrients input from the coastal erosion sustained the 20% of the net primary production of the Arctic Ocean. Well, in contrast to the irreversible coastal land loss, the delta of southern Greenland have progressed over the past decades, and this can be attributed to the increased sediment export from the Greenland ice sheet. And well, the ongoing crossover degradation will likely increase the sediment flux in the coming decades also, and which will until reach the peak sediment like here. And the peak sediment concept here advances the traditional view of periglacial sedimentation by considering the impacts of erodible landscapes and also the different rainfall scenarios from the basin perspective. And here in our projections, the time of peak sediments is confined between the time of peak meltwater, like the blue line here, and also the time of completion of deglaciation, like the purple line here. And the time of peak meltwater is inferred from the global assessment of peak water by Holocene in 2018, and completion of deglaciation is inferred from the projections of glacier extent and permafrost extent in the next 2 centuries. Well, here, one thing I want to highlight is under the stable rainfall and increased rainfall scenarios, the timing of peak sediment can lag from decades to centuries behind the peak meltwater by revoking periglacial and subglacial sediment legacy. Well, we further predict the regime shifts in the sediment transport, which will go through 3 stages. And in the first stage, the sediment transport is dominated by the thermal processes, including the meltwater-driven sediment transport and the thermally activated glacier and permafrost erosion, as well as the expansion of the erodible landscapes with the retreat of frozen landscape, like we can see from the expanded pink area and decreased blue area in the basin hypsometry. And all these processes are sensitive to the temperature, and the exponential increases of sediment transport with basin temperature has been reported in many glaciarized and permafrost catchments. And this overall increase in the erodible landscapes and meltwater eventually increase the sediment yield in the cold regions in the early stage of deglaciation, as we have already seen from the pattern of our inventory. And after the peak meltwater, we will move into the stage 2. And in this stage, the meltwater would make the rainfall events increasingly important in sediment mobilization and transport. Meanwhile, there will be more thermally control landscape degrading into the ice-free landscapes, where the sediment mobilization will be more dependent on the rainfall flushing, like the expanded brown region here. And in this state, the sediment transport will be jointly controlled by the thermal and pluvial processes. And such tendency has already been seen in some Arctic watersheds, like here in a Canadian Arctic catchment. The active layer detachment in 2007 primed the large amounts of available sediment for the subsequent rainstorms and intense snowmelt events. And these events are expressed as a sharp increase in accumulated sediment yields several years after the active layer detachment. And this figure below just gave us another example to show how the loose sediments by freeze-thaw actions stored along the riverbanks are flushed away in a few days later by the rainstorm events. Well, at the completion of the deglaciation, we will enter into the stage 3, where the landscapes are fully ice-free and the meltwater will also be depleted. And in this stage, the sediment transport will be dominated by rainfall. There will be more rainstorm-triggered episodic events like the landslides, debris flow, and also will create a more variable sediment transport pattern like here. And the exhaustion of the sediment supply will eventually decrease the sediment yield. Well, the geomorphic feedbacks, connectivity, and the human activity can altogether make the sediment transport much more complicated. For example, the increased sediment supply from the hill slopes can be disconnected from the river channels by forming the debris fan, and by landscape stabilization, and also like disconnected by vegetation recovery in the coming years. Here in a picture I took from the Karagandaki River Valley in Nepal, we can see such a rapid alternation of the disconnected and connected sediment sources at such a short distance. And the sediment source to sink processes can also be disturbed by many human activities like damming, deforestation, reforestation, and all these activities will can disturb the sediment signal of the warming driven increase in sediment flux from the mountain erosional regions can be completely muted by the increased artificial sediment sinks downstream, and large part of sediment will be trapped behind these dams in the reservoirs. And this, all of these complexities in sediment cascading will sediment modeling and predictions much more challenging and leave a more uncertain future for the delta regions. Well, before the end of my sharing, I want to leave you with 5 key points. Well, first of all, the ongoing climate warming and crossover degradation have dramatically altered the erosion and enhanced the sediment transporting cold regions. And sediment supply can be increased by glacial, paraglacial erosion, increased access to sediment storage, and also by expanded thermochronology landscapes and enhanced sediment connectivity. And since 1950s, more than double sediment flux have been observed in many cold regions, and many parts of Arctic coastlines have been have witnessed the more than double erosion rates because of the permafrost thaw. And well, such increase will not last forever, and the peak sediment will be reached decades to hundreds of years later than the peak meltwater, and the uncertainty can come from the complicated geomorphic feedbacks and rapid changes in the connectivity. Well, along with the completion of deglaciation, the sediment transport regimes are predicted to shift from the ongoing temperature-dominated regime to a rainfall-dominated regime. Okay, so that's all for my sharing today, and thank you all for the attention, and welcome to go through our research work for more details if you're interested.
Yeah. Okay. So good afternoon to everyone. All right. I want to thank Professor Oguchi for inviting me, all right, to share some research work, and I think I'll just go ahead with it. So the title of my presentation this afternoon will be Response of Kelantan Delta System to Late Holocene Sea Level Change, and also present-day human activities, right? Now, okay, let me go to the next slide. It's about myself. Right, okay, my name is Edlic Sathiamurthy. I received my doctoral degree from Nanyang Technological University, Singapore, in the field of hydrology, and currently I'm an associate professor, right, in the University Malaysia Terengganu, right, Malaysia, in the marine geoscience program, and some of my research interests actually coastal plain floods, and also temporary open-closed estuary system, and also into paleohydrology and fluvial processes, right? Okay, so where is Kelantan Delta? So this is the regional map, right, of Southeast Asia. You can see Kelantan Delta is actually at the, all right, at the east coast of peninsular Malaysia, right? And the map shows the river basin boundary, right? Those are river basin boundary, and A is actually a Kelantan River Basin. There are actually three major river basins on the east coast of peninsular Malaysia. A is Kelantan River Basin, B is Terengganu, and C is the biggest one, is Pahang River Basin. But my focus will be on the Kelantan River Basin because of some interesting things to look at, right? Now, Kelantan Delta is actually classified as a wave, what called a delta created by wave processes, right? I mean, wave dominated delta system, right? Now, this is just to show what was in the earliest Landsat image of Kelantan Delta back in 1973. And you can notice that the front part of the delta is actually a sandy coastline, right? And with speeds and all these kind of things, which are typical of a wave-dominated delta, right? And this is a more recent satellite image from Google Earth, right? You can see basically the same thing, but there are some major changes is occurring, especially at the delta front, due to human activities, all right? Now this will cover a bit about sea level change, right? Because dealing with the late Holocene means looking at from the Holocene high stand, which is about 6 to 4,000 years ago, 6 to 4 KABP, and to present day, right? Of course, you can see that it depends on the area of location of research. Sea level change from the mid-Holocene or from the high stand to present day, there are variables, right? Depending on the geographical location. But basically, we can use an average, right? So I'm going to use an average. So back in the Holocene high stand, the sea level was almost 5 meters higher than the current level, right? Then after that, after the high stand, this area, the Kelantan Delta, actually experienced a stepwise sea level drop, right, until the present day. So there's a bit different, about 4 to 5 meters of sea level. Right. So this is an SRTM topography, right? And just to give you an idea, and now the zone A of 1 is actually the high ground, right? Those green patches are actually more than 10 meters. So they are actually above the high stand level. And number 2 is the paleo delta. You can see the faucet of the delta, right? Later on, I will show you in the LiDAR image, right? Right, and they become very clear. So number 2 is the faucet area. And number 3 is the recent paleo delta, right? And then number 4 is the present day delta. And 5 features that shown in that number 5, parallel to the modern day shoreline. You can see ridges, right? Those are actually beach ridges, right? Which is indicating what I call paleo coastlines, right? All right, and and then of course this coast paleo coastline are actually in a retreating what I call it's actually retreating because of sea level drop. And then number 6, right, you can see these are flat areas between ridges, and they are actually formerly paleo lagoons. Now of course it's filled with sediment, right? It's no longer a lagoon, right? And basically in terms of land use, they are basically used for planting of rice fields or paddy fields, right? And then number 7 is the present day Spits, right? And Barrier Islands. And number 8 is the Kelantan River itself. Now, I just want to show one of the profile, which is number 2, right? Now, this is a LiDAR image of the lower part of the Kelantan River Basin, covering the Kelantan Delta area. And as you can see, the different position. Now, the faucet you can see right in front here, right? This part, actually, this is the Paleo Delta during the high stand, right? And of course, I don't do the age dating yet, right? I need partners possibly for age dating, right? Just based on the sea level curve and also the topography, right? The topographic data. But the LiDAR data do give very good precision and accuracy in terms of elevation, right? Now, so this is the former the high stand, the delta during the high stand, around 4.5 kABP. And then from here, the delta actually shift to here, this position, right? Somewhere in the 2.5 Ka, right? Okay, around 2.5 kABP, right? And from here, it switch position to this. I mark it up with all this line here, around 1.8 Ka before the present day position here. So there is a clear from the LiDAR data, we can actually see this delta is the previous delta of the high stand. Then it moved to the position number 2. The position here, and then switch to here, and then later on to here. All right, and of course this is corresponding to sea level drop after the high stand. Of course, how do I identify them as delta? Because of the ridges, right? In wave dominated delta, you have ridges, right? Ridges you have sand ridges. So these paleo ridges are actually, or strand planes rather, there, and you can see this changing of the what I call the position of the strand planes actually indicate the changing of the delta itself, right? And if you look at profile number 2 here, right, if you draw a cross section from the backfill area here, it's very flat. This is a backfill area, and this is a strain plane, and then you have backfill, all right, and there's another strain planes here, and then finally to the modern day position. All right, later on there's another one that's a bit more clearer, all right? And this is just to zoom in to look at it. And of course, there are a lot of details can be seen from the delta system here, not just the changing position. Now, these lines here that are drawn here are actually the strain planes, right? The strain planes. So you can see that the first delta here, we have is paleo coastline here, right? And then the second one have is paleo coastline here. You can see there's a strain plane here. And then from the second, what I call the third position here, you also have this sets of strain plane, and then finally here, right? So this actually can correspond with the sea level change, because each of these position actually they have means starting from here, this is about 5 meters above the modern sea level, mean sea level, and then going down here less than 5, and of course this is the lowest, which is just beside the this is at the modern day coastline. All right, and of course the one thing is needed here is of course the age dating take samples, right, and to age date and to know each of these delta here, when did actually this delta develop, right, and to actually know how it evolved or change our position in response to sea level drop, right? Okay. And of course, this is a current day, present day. Now, there's another sampling set, but I cannot really identify this properly because it's not that clear even in the LiDAR imaging, LiDAR data. Yep. Now, apart from we can see the changing position of the delta in response to sea level drop, right? You also can see that actually there's also an effect on the what I call on the Kelantan River itself, right? We start with here. This is the modern day Kelantan River, right? The modern day Kelantan River, and you can see there's a paleo delta complex here. There's a lot of meander belts in this region, right? And there's also, you can see that this is the previous Kelantan River discharging on this side of the delta, which is more towards the eastern side, all right? And there's a very clear semi-abandoned channel. It's semi-abandoned because part of the channel is still active, but it is a modern day incision into the older river bed. But the river itself, the main river itself, has shifted position to here. In fact, somewhere in the middle here, right, which are not shown in this image, you can see the Kelantan River actually shifting from this position to here. There's another estuary somewhere here and here before actually you reach a modern day position. And this is also in response to the shifting, what I call it corresponds to the shifting the delta and the sea level drop, right? Okay, this is the more detailed image, right, of the abandoned channel, right? Okay, I think I'll go to, okay, then you can see the meander belt, and I have a cross section here, right? So here, this position A to B here is actually the whole river, right? Previously, the Paleo River, right? And they'll have sediment island in the middle, but today, the modern day river is just a small incision on the previous river bed, which is a sign of sea level drop, incision caused by sea level drop, right? And just to imagine that if this, what it will looks like, okay, let's say during the high stand, how does Kelantan delta actually looks like, right? Of course, this is educated guess, right? So it'll be something like this, right? And quickly, okay, this is the cross-section view. Now I'll go straight to the human impact. Now, of course, modern day, the impact is basically erosion of the delta front caused by human activity, all right? Now, of course, we also have sea level rise, right, in this region, okay? And okay, back in 1985, you know, they actually built a breakwater somewhere in the eastern side of the delta, right, to enable navigation of fishing boats, right? So they built a breakwater like this. And as a result of that, it actually disrupts the longshore transport. The longshore transport is going from the east to the north, all right? Okay, longshore transport, and you can see by 2005, a very remarkable erosion here, right? It actually retreated about 400 meters in 20 years, meaning around 20 meters per year, all right? This is back 2015, 19, and this area, 1985, sorry, the image is not clear, right? In 1985, landslide is a bit coarse, right? And you can see, right, the yellow line is 1985, this is 2009, 2015, 2019, 2020, and means it retreated around 450 meters in 12 years. And all these are actually can be traced back to one of few factors. One of it is the breakwater and also the change in sediment supply from upstream, which I do not deal with in this topic today, because due to a lot of development and land use changes. Thank you. All right.